Okay, so now we're going to calculate the magnetic field of current, well, the magnetic field due to a loop of current in this particular case. And here we have a single loop of current, okay? The current is going around this way, so the magnetic field is going to come out of the board. We want to calculate the strength of the magnetic field, and the first case we'll do it for right in the center right here. The next case we'll do along the axis of symmetry above the loop of current. But again, we can see the magnetic field. The current wraps around the magnetic field. The magnetic field goes in the direction of my thumb using the right hand rule. So there is a diagram of that magnetic field. Here's an actual visualization of the magnetic field using metal filings, iron filings, and a loop of current. Okay, let's calculate the magnetic field in the simplest case at the center of a loop of wire. We know that, according to the Biot-Savart law, that dB is equal to mu 0 over 4 pi I dl cross r over r squared. In this particular case, we can simplify this a little bit because dl cross r, if we look at this, dl is going this way, r is always pointing toward the center, so sine theta here becomes a sine of 90 degrees. The dl vector is always perpendicular to the direction that we're looking at. We're always looking toward the center of the circle when we're calculating that magnetic field right there. So this sine term can go away, all right? And we're going to integrate these little parts of dl all the way around, okay, from 0 to 2 pi, and calculate the magnetic field that way. So we have B is equal to mu 0 for pi. We're integrating. I is a constant that can go outside. R over r squared becomes 1 over r. Okay, so that can go outside. And all we're left with is d phi right here, which we're going to integrate from 0 to 2 pi. Very, very simple right here. We integrate d phi over 2 pi. Okay, so 2 pi minus 0 is going to be 2 pi. The 2 pi here divided by 4 pi becomes 1/2, and this becomes the expression for the magnetic field at the center of a loop of wire. So that's really straightforward. That's really quite easy. That's about the easiest integral that you can have. If you have d phi and you're integrating that, you get phi, which is going from 0 to 2 pi, so it's 2 pi minus 0. Nothing easier than that. What about the magnetic field above and below this loop of current? We've already seen that in looking at the different diagrams, that as we get away from the center right here, the field lines begin to diverge. The field lines are spreading out more and more, so the magnetic field is getting weaker and weaker, as we would expect as we get away from this. Now, the simplest case was at the center of this loop of current. Now we're going to look still along that axis of symmetry. So if we put a axis right here, right at the center of this loop, we're looking at the magnetic field above the center of the loop, directly above the center of the loop. And now we're going to calculate the magnetic field again. So again, at the center of the single loop of current, mu 0 times I divided by 2r, r being the radius of the loop. If we had multiple loops, as we're going to see with the solenoid, we would simply just increase the magnetic field according to how many loops we have. 2 loops would create twice as much of the magnetic field. Okay, so let's look at the more complicated case. So instead of looking right here, we're now looking at the magnetic field up here. Okay, so basically, this loop of wire is going to sit in the XZ plane. Okay, and the Y direction is going to be along this axis right here. So here is our scalar version of the Biot-Savart law. Okay, again we have dl sine theta over r squared. In this particular case, dl goes this way. R is pointing at a 90-degree angle with respect to dl. I mean, even though it's not pointing perpendicular to this plane, it is perpendicular to DL. So sine theta can just become 1. Here, r squared represents the distance from DL to this infinitesimal amount of magnetic field. Okay, so this right here represents the hypotenuse. All right, that should be r. So y is this distance right here, r is this distance right here. So to get r squared by the Pythagorean theorem, the hypotenuse squared is equal to the adjacent side squared plus the opposite side squared. And that's what we have right here. Okay, so now we're at this point. We're going to make a little adjustment here. We know from the right-hand rule that the magnetic field is going to point in the y direction. Okay, so we're only concerned about the y component of the magnetic field. So instead of calculating dB, which over here is going to point this way, over here is going to point this way, and having to cancel out all the other contributions in the x and the z direction, we'll concentrate on the y direction only. So here, dBy is going to be dB times cosine theta. Okay? Y cosine theta. Theta represents this angle right here between this vector and the y direction. So the y component is going to go by dB sine of that particular angle. Okay? I'm sorry, cosine of that particular angle. I'm still used to the sine. So this sine has disappeared. Okay? And this cosine is completely unrelated. It's related to the fact that we're looking at the y component. Normally with y component, yes, we do use the cosine of the angle, but that's what theta is with respect to the x-axis. This theta is with respect to the y-axis. Yeah, a little complicated. So now this is our equation. We know that cosine, okay, of theta, cosine theta is equal to the adjacent side, so that's the r right here, divided by the hypotenuse, okay, which is right here. And taking that as a substitution, that goes up here, that'll give you this expression in the denominator. So again, we're left with 3/2 in the denominator right there. So when we go to integrate this, I is a constant that can come out. We're going to integrate this expression right here. Again, I should be out of there right there. But we're going to integrate with respect to DL. So really, looking at r is a constant, y is a constant. Well, those can come out of the integral too. And we're actually left with a pretty easy integral. We're left with DL. So if we integrate all the way around here, okay, each little small part of DL is equal to capital R times d phi. So we integrate all the way around there, and that total length right there becomes 2 pi r. That's just the circumference of a circle. If we're integrating over the total length of this loop, we're integrating over the circumference of a circle. Well, that integral was pretty easy. I saw that 3/2 there. You immediately say, oh, this is going to be a challenging problem. So we simplify the expression. Okay, we've got 2 pi here, we've got 4 pi there. That'll, cancel out to become 1/2. And our expression looks something like this. And to test this, we understand as we go further and further up, our expectation is that the strength of the magnetic field should get weaker. There's y. As y gets larger, the strength of the magnetic field goes roughly by 1 over, if we take a look at r as being small, but y squared to the 3/2 is basically y to the 3rd. So essentially, this field is going to get weaker and weaker by 1 over the cube of y, as you go further and further up, as r becomes small compared to y, sort of goes in that direction. Okay, so again, we got an expression for the center right there, fairly simple expression for the magnetic field at the center. And then the magnetic field along the axis of symmetry, a little more complicated. Now, if we wanted to calculate the magnetic field anywhere to the side, that's when you probably want to stick with numerical analysis. I can't come up with a good analytical expression with that using calculus. That would be a bit of a challenging problem. Okay?